Alright, so once we understand the algorithms, then we implement it in the Java using Java code. Again, let's say this structure itself is learn the algorithms here. You don't need to use Java to write BST. It can be any programming languages. But for this class, we just use Java as the tools. Okay, so we initialize count to 0. If loop not equal to null, check if it's empty or not. If not empty, then we start to create a stack. Right, instantiate stack. We're going to instantiate stack to hold the nodes that we want to visit. We set the current node. And we push the root to stack. Right, home. Now, if the root is not empty, then we're going to get into the loop, which is the current node equals to hold the top. Look at the top. Let's just look at the top of stack. Now we're going to pop and increment it. That means we already visit. If current node dot get left not equal to null, then we push the left nodes into the stack. Else we're going to if get right not equal to null, then push the right node to the stack. And we keep looping that again and again until, because every time we loop we do at the top and pop and increment the top count. Then if we keep popping to the left, then it's going to be empty. That means we already count all the nodes in between and return the count. Now the question is, should I use recursion or iteration? We look at two forms, right? Get the size. We said, is the depth of recursion relatively shallow? Is it shallow? Yes. Is the recursion solution shorter or fairer than the non-recursive version? Yes. Is recursive version much less efficient than the non-recursive version? No. We know that recursion is not efficient. So it said this is not validated to use recursion, and the key reason is make the code shorter and clearer to read, and make recursive is not too depth, right? So it's shallow. So that's the author opinions. Want to use recursion to trade off with efficiency with the click on. Alright, so we're going to look at how we're going to implement contains, get, add, remove, iteration, set, and get next. The contains operations. So let's look at the contains first. We're going to use the recursive approach called recursive contains, which pass the elements we are searching for and a reference to a subtree in which to search. So this is like an approach that we apply on a size. So first check to see if the element searched for is in the root. If not, compare the element with the root and looks in either the left or the right subtree you want to go to. Because left subtree is going to be smaller than the root, or equals, right? Right is going to be greater. So when you search this way, this is like a binary search. Because you split in half, right? So this is not linear. So let's look at how we implement contains. So we have contains that pass the element in, and then we call recursive contains that you pass the key, element is the key, to find, and then the root of the BST. So to the recursive contains. And recursive contains, we have to first check, right, the same principle that we apply for size. If it's null, then it's return false. We never contain it because the tree is null. It's empty tree. Else, we have to compare the elements, right, or the key to the actual node, which is get info, right? Which is get the element values. After we compare, now if it's the root, then we compare the root, we pass in the root here, right? The parent, then we know if it's less than 0, then we have to recursively pass the left node to search and pass the key in. As it's going to do the same recursively doing this. Else we go pass the right because it's having to be greater than 0. And since we assume that this BST has no duplicate, that's why we didn't do less than equals. When it's found that it equals, we return true because it's no duplicate. Such return true. So that's how we implement contains. So let's see how we'll get. It should be the same principle, right? Instead of returns boolean, we return the item itself. So pass called recursive get the key and the root in. And if it's null, then return null. Else if compare less than, just pass in a get left. Else get right. Returns instead of true or false, just return the info itself that you found. How about add? We're going to use the node, right, and use linked list to implement this BST. We first create a new node when we want to add 5 to an empty tree, and then we point 3 to the root, which is 5. We add 9. First, before we add, we have to compare the root. Then we know should we set right or set left of the root. In this case, root does set right to new node because it's greater than. Now we start to add 7. So first we have to compare to the root. 7 is greater than 5. Then go to get right and compare the get right again. It's less than 9, then we set that since this is the leaf. When we get the null back, then we set the leaf to right left. But this has to be recursively called. Add 3, same comparative root. Less than, then set left. Since get left of the root is null, then set left to 3. Add 8. Same 8 is greater than 5. Get right is not null, then compare. 9 and 8. 8 is less than get left then. Get left is 7. It's not null, then we compare. 7 and 8. Then 8 is greater than, then get right of 7. Which is null, then we set right of 7 to 8. Add 12, compare the root, 12, get right of root, which is 9, then compare 9 to 12, and get right of 9, which is null, then set right of 9 to 12. So that's what we need to implement. But how we do that in recursive version? So we need to add the methods, right? To have elements to add and recursive add. Then this principle should be applying to the same as like we do get, right, or contains, because we keep comparing. After we find the location, we just do set to insert. So let's look at first check if tree is null. If it's null, that means the new node is a tree. So tree equals the new node. Right, instead of return false, just return tree equals the new node, or just set, not returning anything, set. Else that means we start to compare. If it's less than, we pass that in. Right, the left, and it's recursive do the thing again until we find the location, set it. If happen to be greater than, then we pass the set right. See that we do treat the set left right here and call recursively add. Recursive add pretty much is going to set the last node, but we want to, after we set that, we want to send a link back. Like if you this is only happen when the root is empty. The rest happen here, set left and set right. Because it's going to return the tree itself back. Once you set. So this pretty much just keep comparing it to the leaf and return the leaf back to set. Because if it's not less than, if it's not greater than, then it's return 3, which is the leaf. So this is explaining. So first, root equals to recursive add. 13 is the key that we want to add, and we pass the root, which is 7. And you can see if it's not equal to null, then we do else. Else we compare. We know this has to go to the right, so we do the set right. Right, we have to do compare, go to the right, not the left, go to the right, we do set right, and pass recursive again, which is pass 7 in, right? And then 7 compare again to 15 because this is recursive. Then sorry, we do 13, 13 compare against, we compare 13 to 7. We know we have to pass the right in. And then 15 compare again to 13. Then we have to pass the left. And 10 compares to 13. Right, so we get to this point, right? Left. Recursively elements, which is 13, tree that get left is 10. So it's called cell again. Do we have, so we have 10 and 13, right? 10 and 13, we know that this is going to be set left, right? No, set right, because 13 is greater than 10, right? So at that point, we're going to set 13. Because we try to get right again, it's return null. Right, if it's equals to null, 3 pretty much equals to the 10. We return 10 back.